Hello, and welcome to Physics 2, Lab 4, Circuits. Introduction. The purpose of this lab was to design circuits utilizing various circuit components, then to observe the effect these components had on the electric potential of the circuit and record the corresponding current when impacted by these circuit components. Then we would utilize these measurements to determine the charging time of a capacitor and compare the ideal time to the recorded time to charge and discuss the differences and how they could occur. The physics principles utilized in this lab are Kirchhoff's loop rule, which states the sum of all electric potential differences in a closed loop is zero, and Kirchhoff's node rule, which states that the current floating into a junction must equal the current flowing out of the junction. The equations used in this lab are Ohm's law, V equals IR, the capacitor's equation, which is C equals Q over V, the parallel resistance formula, and the resistance in series formula, as well as the given equation of the time to charge. We had 3 models in this lab. The first 2 are observational, and they are made up of the 2 circuits we made physically in lab. Circuit 1 consists of 2 1.5 volt batteries. It has 2 resistors in series, the first of which is 47 ohms, and the second which is 100 ohms. Circuit 2 utilizes the same 1.5 volt batteries, but this time it has a 20 ohm resistor in the form of a light bulb and a 200 mF capacitor. The computational model utilized the recorded measurements from these 2 circuits and organized them into a calculated value spreadsheet, which graphed the voltage over time and calculated the time constant. Here are the pictures of the circuits built in lab. This is circuit 1. As you can see, there is a resistor here attached to the ammeters, which are attached to the batteries, which is attached to another ammeter over here. In here we have circuit 2, which is the capacitor, the bulb, all looking nice and sharp. Experimentally, in circuit 1, we calculated the resistances of each in real life. The 47 ohm resistor actually contributed about 46.7 ohms of resistance. The 100 ohm resistor was a little bit more at 101.4 ohms, and the ammeter and the wire both contributed about 0 ohms of resistance. In circuit 2, we calculated the time to charge of the capacitor as 24.3 seconds and the time to discharge at about 25.6 seconds. The results from the recorded values spreadsheet is this graph right here of ln V over V naught versus T. As you can see, we have a decreasing slope of the best fit line, and utilizing this slope and setting it up in the equation the slope equals -1 over RC, we are able to solve for RC as 21.09 seconds. Discussion. What if the differences between a simulated and real-life ammeter is that, in reality, the ammeter will be affected by the surroundings? The same can be said for real-world circuit components, as they'd be impacted by interior degradation and other forms of wear and tear. The simulation offers a perfect scenario, while in real life there are many factors that could affect the results and contribute sources of error. Similarly, when discussing a simulated capacitor, it would charge near instantly in a simulation, as there would be no resistance between the battery and the capacitor. In real life, however, it would take the capacitor much longer, as wires do offer a semblance of resistance. However negligible it may be, it will impact it slightly and not be as near perfect as the simulation, as well as the capacitor being affected by the same physical wear and tear as in question 1 for the discussion questions for the resistors and the ammeter. In real life, there's just more opportunity for outside agents to affect our circuits. And in conclusion, this lab showcased the impact different circuit components have on the potential difference of a closed loop. From this analysis, we were able to determine the physical time constant for the capacitor present in the circuit. Thank you for watching.